Hello, everyone. All right, we're going to continue along with what we talked about last time, and specifically, we're going to go into more details of measurement. We need to separate the ideas of measured quantities versus counted or exact ones, which are more numerical definitions. And we need to talk about how we're going to deal with the concept of error as part of this. We also need to deal with the idea that I think some people who make up these slides are trolls. So, as evidence here, let's try it. The question in terms of an exact number is things you can count. So, coins in your pocket, markers on the table here. The example that the people who made this up chose was this. So let's ask the question, everyone. How many balls are there? Trolls. Okay, so measurements. Specifically, this is our issue. Counting does not have errors. A counted number is one that you can observe the individual parts of, and there's no error involved unless you're just too young to know how to count or mentally impaired for some reason. But that's not an issue in our current topic. If I have to count the coins in my pocket, there's no error there. If I have to count the number of balls on that first screen, there's no error there. I can count that. So we don't have to deal with error as part of a counted number. We do have to deal with it when we bring in measurements. Measurements use a tool to compare against because we can't count the quantity involved. So as a result, that comparison, be it optical, you looking at a ruler, or electrical, something like a balance or other instruments that we might use, is subject to making errors. And so the topic of significant figures specifically exists so that we have a way to limit our errors and they don't make our answers any worse. They also can't make them any better. So this is a good time to introduce the concept. Your measurements do not get better or worse with math. Ever. They don't. So the quality of what you measured is not going to change just because you decide to use a different scale. So as long as you use the same tool to measure things with, it doesn't matter what you convert that measurement into, it still has the same error as a percentage. So we can't ignore that. We can't get better or worse with doing math on that. And we'll get to that later on. Okay, so the easy example, and one that we typically do in an in-person lab, is just looking at measurements of length, because we can give you two different quality rulers and you can see the difference. But we're not in an in-person lab, and at this rate, given how many people don't wear masks, we may never be back in an in-person lab. So let's get used to dealing with things on screen, shall we? So here is one example of a ruler. And if you remember, what you may have seen in the lab already, but if you haven't, when we look at measurement tools, we have two options. We have two things we can say. One, we can say the digits we're sure of, which is that we know this object is greater than 4 and less than 5. So that means I'm absolutely sure of this, the 4. I'm not sure. I don't have a mark to tell me where we are in between. So that is an estimation digit, which I then have to come up with myself. So I'm going to say it's about halfway, so I'm going to call that a 5. And then a centimeter. So I have the digits I'm sure of, in this case is only one estimation digit, and as I said in the previous video, the units. Very important, keep the units on things. Okay, contrast, better ruler. Okay, I now have a better tool to work with. So now I can say with certainty that this is 4.5 here and this is 4.6. So I can say these are certain digits. I know it's bigger than 4.5 and less than 4.6. So then I'm guessing in between that, and it's harder to see at this point, but I'm going to just say we're halfway, and that's my estimation digit. So your measurements will have all the digits you can actually see based on the tool you're using, and you will have one estimation digit for yourself that you have to make a judgment call on. So that is not that tricky, but what happens as you're getting used to this at first is people tend to just forget that part and go, okay, it's about 4.5. Okay, about doesn't cut it. The point of measurement is to get every bit of information that we can, so that means that last digit is important. Okay, now, what if we're right on one of the marks? Then we have to basically put a 0 in place, because we know that we can be sure of the centimeter here. We can be sure of the 3. But because of the tool, we get that one estimation digit. So as far as I can see, it looks like it's right on the mark. So to keep this in line with what I saw in the previous one, I'm going to still use that extra estimation digit, but I'm estimating that it's 0. It's 0/10 of the way across between 3 and 4. So this is a very common error, to leave off a 0 when it looks like you're right on the mark. Don't do that. That last digit is important when we do calculations later. Even if it's a 0, we need to know it's there. So the concept is one of significant figures, and that is when we look at measurements, what digits do we consider to be real and what digits are just placeholders or otherwise not useful to us. This is our measurement error in a way. Significant figures allow us to keep from overstating or understating what we actually know. So here we go. There are some very simple rules here. 1, any non-zero digit. You're not making that one up. The question is only, the real problem with significant figures only happens with zeros. Anything that's not a 0, the implication is you measured that. So the zeros are our problem, and it depends on where they are. But anything that's non-zero is a significant figure. Okay, so this is a relatively hard to read thing, but very quickly, and then we'll go through them individually. Anything that's non-zero, any 0 between the zeros. So if I measure something that's 205 degrees, that means I'm sure that's 0 because I had to be that good to get to the 5. So we have to be able to say that a 0 within a measurement between non-zeros actually does count. It's real for us, a significant figure. At the end, yes, but only if there's a decimal place. So in these cases, with a decimal place that terminates the number or a decimal place that has zeros after it, they count. And what we're going to be doing is counting those digits up, because we have to keep track of that for our eventual answer if we're going to do calculations. So that's what this column is. How many digits do I have that count? 2 of them. Here I have 5 of them, and so on. We haven't talked about scientific notation yet because it doesn't make any sense to talk about it before you have significant figures. But when we do, yeah, anything written on this part is significant. But the point is, it shouldn't be written there because there's a decimal there. It's going to basically follow the rules of C. If there's a 0, it's going to be after a decimal. So we'll talk about that in a separate video. When they don't count is if they're at the start, because that's just placeholding where the decimal is. So those 4 zeros at the start of this do not count. There's only one digit there that does count. And then afterwards, well, there's our question, is do they count? And we're not sure. We need more information. So most of the time we're going to assume no, but we might get better information to help us. All right. So let's take a look here. Anything that's not 0. As long as it's a measurement, significant. Remember, this is about error. Significant figures really don't exist if you're not talking about measurements, because numbers don't have errors. Measurements do. So that's why we have to do this, and that's why we have to pay attention to these rules and what we're going to do with them in calculations. So each case here, literally I'm just counting up the digits because there's no zeros here. I can say, all right, well, 1, 2, 3, 4. Okay, 4 significant figures. Bottom one, 1, 2, 3, 4, 5 significant figures. And that's what we need. So we're going to have to keep track of that if we're going to do calculations with this later. Okay, zeros that are not between, zeros that are between other digits. So that means that one, those two, that one, and each of those. They're in between. They count. As it turns out, this is actually wrong because this one counts too, but they ignored that. So this is a typo on the slide. Should be 4. But the point in this question is, do those zeros count? The ones that I've underlined, yes, they're between two non-zeros, therefore they have to count. Things at the start, no, that doesn't count. That doesn't count. That doesn't count. Things at the end, if there's a decimal, it does count. That's why I had to correct that. But it doesn't matter if they're split, like the bottom one here. It could be a 0, then a non-zero, then a 0, then another non-zero. They still count. So all these 1, 2, 3, 4, 5 digits, they all count. Okay, if there's a decimal, notice this looks exactly like the one before it, and it does count. Yes, we have to actually count the ones after a decimal place, even if it's just a terminator decimal. So all of these are digits that we care about, and they count, and they're going to give us better answers if we're doing math on this for conversions, for calculations of things like area and volume. We need those digits, because if we don't have them, we have to take back the accuracy of our answer, and that can be a big deal. And we'll talk about that as we get to the topic. At the start, no. So that means basically these don't count because they're at the start of the number, before the first non-zero digit. Again, the one after a decimal, yeah, it counts. So that's why that top one is actually 3. The others are all non-zero digits, so 2 and 2, 2, 3, 6 and 1, 3. So this is not hard, but it just takes a little getting used to, especially with the zeros. Okay, big numbers. Yes and no. If you're just given a big number with a lot of zeros after it, then the assumption, keyword assumption, is that it's not significant. But with more information, we may change our mind on that. And that is things like the tool that was used or the error bars for the measurement. So that is not written in stone. That one is one that's a little bit of a variable, but your book's not getting into that, so neither will I. If we know we measured that last place, the ones place in a measurement, and we know that that's our last significant digit, then we can put a decimal after it to make it clear. So if I wrote this as 500, the question is, all right, is that plus or minus 100 or plus or minus 1? The decimal here tells us that the ones place is a significant figure. Without it, we would assume no, and it would be only one significant figure. Now, we haven't done scientific notation yet. We're going to come back to that. But as we do, the only thing to keep in mind with scientific notation is every digit in this part is significant. Every one. So that first one, 4.90, 3 significant digits. 8.0, 2 significant digits. 6.0330, 5 significant digits. So for scientific notation purposes, all you need to know is the first portion, everything is significant. We'll come back to that in scientific notation in the next video. When you're converting to scientific notation, again, if you're going to convert anything, you need to know how many significant figures you started out with, because that's going to limit your answer no matter what we're doing with it. So I needed to basically work out this third column before I did the second one. So in the first column, I have 2 zeros, but there's a decimal, so that means 3 significant figures. Here I have 5 zeros, but there's no decimal. That means 1 significant figure. Here I have 2 after the decimal. They count, and 1 before, and it doesn't. So that means 3 significant figures. And then we convert to scientific notation. Now, big problem we're going to have with scientific notation, your calculator does not understand significant figures. So you have to be careful with that. Your calculator will take every one of these down to 1 significant figure when you convert it to scientific notation. Be careful. That's why you need to work out this third column before you do the second one, because you may have to correct your answer on that. Very frequently, you'll have to correct your answer on that, just like these. Your calculator will give you 5 times 10 to the second, 3 times 10 to the minus 1. Both of those are wrong. So you have to be aware of significant figures yourself before your calculator changes your mind. Okay, back to our trolling. Exact number. How many balls are there? Again, counted numbers are easy. That's one type of exact number. You can count them. The other is when we have a definition. Now, what does that mean? For our purposes, we use them as conversion factors, but it means that we're looking at 2 quantities that mean the same thing. So, easy one to remember is like 1 foot is 12 inches. You didn't measure those. They're a definition, which means it could be this, 1.00000 feet, and, 12.00000 inches. The point is, this is not an error. Conversion factors are not measurements. They do not have errors. So we don't have to use them to limit our answers when we're doing calculations. So that's the important thing here. You didn't count them, but the point is they're still not measurements. Measurements have errors. No other numbers do, whether they're counted numbers or whether they're actual equalities, conversion factors. So those do not limit your answer anywhere else. Okay, so practice. Pause the video and see if you can answer these. Okay, so when you unpause it, we'll go back to it now. First and foremost, things you can count. Okay? Things like that. That doesn't have significant figures. There are no errors there. So we call that an exact number or a counted number, depending on which textbook you're using. Conversion factors, where there's an equal sign in between 2 things that represent the same quantity. Again, that's exact. There's no errors involved there. The other things here just have 1 quantity. They're measured. Time, volume. There are going to be errors there. So those we have to keep track of significant figures. So, bottom one is easy. Again, scientific notation. Just take that first piece. There's 2. And the abbreviation sometimes SF. Top case, I have zeros. I have 1 before. Zeros at the start never count. They just hold the decimal in place. And I have 1 after. Zeros after a decimal do count. So that means I have 3 significant figures here. So that's how we do them. In terms of calculations, again, counted numbers and equalities, conversion factors, do not limit our answers. So we don't have to consider significant figures for those things.